The 362,880 futures. Why Monte Carlo strikes out. A case for ParaDEVS in high-fidelity simulation. Imagine a baseball manager sitting in the dugout staring at a lineup card. They have 9 players. The goal is simple. Arrange them in the optimal batting order to maximize run production against a specific opposing pitcher. Mathematically, this seems straightforward. It is a permutation problem, but the scale is deceptive. To find the perfect lineup, you have to evaluate every possible combination of those 9 players. That is 9 factorial. That is 362,880 unique lineups. To know for sure which one is best, you cannot just guess. You need to know the expected run production for each of those lineups. And this is where modern computing hits a wall. The standard approach is the Monte Carlo simulation. It relies on the law of large numbers. To get a statistically significant average for just one lineup, you cannot simulate a single game. You might get a lucky fluke. You have to simulate that same lineup 10,000 times to smooth out the noise. Now do the math. 362,880 lineups multiplied by 10,000 trials per lineup equals over 3.6 billion baseball games that need to be simulated. This is the bottleneck. The computer spends months just rolling virtual dice, recalculating the same physics and probabilities over and over again just to find a stable average for one batting order. Current predictions suggest this brute force method would take over a year to complete. There is a better way. It involves swapping the brute force repetition of Monte Carlo for the structural elegance of ParaDEVS, Paratemporal Discrete Event System Specification. We still iterate through the lineups one by one, but for each lineup, we don't roll dice 10,000 times. We build one comprehensive state tree. Here is how ParaDEVS handles lineup. 1. The root. The game begins with 0 outs. 2. The branching logic. When a batter steps up, ParaDEVS doesn't pick one random result. It simultaneously generates branches for every possible weighted outcome. Walk, single, double, triple, home run, and out. 3. The tree expansion. These branches extend forward, creating new game states. Runners on base, outs recorded. The system tracks the probability mass flowing down every branch until 27 outs are recorded on every leaf of the tree. Instead of playing the game 10,000 times to guess the average runs, ParaDEVS calculates the exact expected value of that lineup in a single execution. The workflow changes dramatically. We generate 362,880 separate trees, one for each permutation of the batting order. Because generating one ParaDEVS tree is exponentially faster than running 10,000 Monte Carlo trials, the total computational time collapses. Monte Carlo, billions of noisy trials, runtime, greater than 1 year. ParaDEVS, 362,880 deterministic trees, runtime, hours. Once the trees are generated, it is trivial to search the results. We instantly identify which tree yielded the highest expected runs, the highest floor, or the most consistent performance. This approach delivers a speed up thousands of times faster than traditional Monte Carlo methods, transforming the scale of what is computationally possible. In complex systems, whether it is optimizing a supply chain or setting a batting order, we cannot afford to rely on the law of large numbers when the sample space is this vast. Monte Carlo asks, if I play this lineup 10,000 times, what is the average? ParaDEVS asks, if I play this lineup once, what are all the possibilities? For the baseball manager, the difference is waiting a year for an answer, or having the winning strategy ready before the first pitch is thrown. ParaDEVS not only accelerates computation, but also provides greater efficiency, accuracy, and adaptability than traditional Monte Carlo simulations. We will demonstrate these advantages in upcoming videos.